Well, I'm going to go ahead and start the recording. The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@ybcc.edu and I will respond as soon as I can. All right, so today, eventually we're going to get to section 9.3, but first I have a couple of questions to answer for people that email them in. While I'm thinking of it, I want to remind you that Monday is a holiday. It's President's Day, so there will be no class meeting on Monday, no office hour, no nothing, okay? All right, anyway, so let's take a look at questions that came in from section 9.2. And this is problem number 9. The instructions say, evaluate the expression. And we have in parentheses, negative 343 to the 1/3 power. Now, I want to point out that the person that asked for this, the answer that they put in was not real. This is real because we're taking an odd root of a negative number. If it was an even root, then that would be correct. It would be, not real, but we can take an odd root. So we're taking the cube root of negative 343. So basically, this is the same thing as the cube root of negative 343. Now, I'm going to take negative 343 and I'm going to break it apart. First of all, I'm going to pull out that -1 factor. Let's see. 343, what goes into 343? Well, let's see. 2 doesn't go in, 3 doesn't go in, 5 doesn't go in. How about 7? I think 7 goes in. Let's try 7. So we've got 343 divided by 7. Yes, so that's 7 times 49, which is 7 times 7 times 7, or -1 times 7 cubed. Okay, so this equals the cube root of -1 times 7 cubed. The cube root of -1 is -1. The cube root of 7 cubed is 7, so we end up with -7, and nothing is underneath the radical. It's just -7, period. All right, we've got one other question that came in. This is also from section 9.2, number 29. Give me a minute here to get this set up. Okay, let's see here. 4781. Giovanni, can you hear me?
Yes, I can hear you.
Okay, I just wanted to make sure because you're the first person that's come this morning, and in the other class there were problems with the microphone, so just good, thank you. All right,
okay.
Carrying on here. Let's see, we've got this class and we want that one. And section 9.2, number 29. Okay. All right. It says use rational exponents to simplify the radical. All right. So we've got the 26th root of 7 to the 13th power. Okay. Now, if we wrote this in exponential form, we would have 7 to the 13/26th power, which is 7 to the 1/2 power, which is the square root of 7. Now, again, I'm looking at the answer that the student put in there, and they had this. They had 7 to the 13th power, and then that raised to the 1/26th power. And that is a correct first step, but that's not the final answer, because a power raised to a power, you'd multiply the exponents together. So eventually, and then you'd put it back in radical form, okay? So you were on the right track, just didn't go far enough. Okay, Giovanni, any questions from you from section 9.2 before we go on?
No, I think I did pretty good on the homework.
Okay, so now we're going to take a look at 9.3. And one of the things you missed, just a reminder, Monday there's no class. It's a holiday.
Why isn't there a meeting on Monday? What's Monday?
No, it's President's Day, I believe.
Oh, okay.
Yeah, President's Day. Okay.
All right, thank you.
So we're going to take a look at section 9.3. And the first thing I want to do is go back and look at a couple of the formulas, shortcuts for exponential notation, and then show you the equivalent in radical form. And if that doesn't make sense, just hold on and hopefully it will as we look at it here. All right, so yesterday we looked at the idea that a product raised to a power, you would apply the power to each factor inside the product, okay? What if I had a product raised to the power 1 over n? Then that would be a to the 1 over n times b to the 1 over n. But what if we took this and rewrote that in radical notation? That would be the nth root of ab equals the nth root of a times the nth root of b. That's a really sad looking radical sign, even for me. So what that tells us is if we're taking the root of a product, we can form the product of the root of each factor. Okay, so we'll be using that rule today. There's another rule I want to look at before we start looking at examples, and that is when we have a quotient to a power, we apply that power to both the numerator and the denominator of that quotient. So let's say we had a over b to the 1 over n power. That would be a to the 1 over n power divided by b to the 1 over n power. If we were to take that and write it in radical notation, we'd have the nth root of the quotient equals the nth root of the numerator over the nth root of the denominator. Now, these two rules, we already actually used in a previous section. We just didn't talk about it much. For instance, if we say, what's the square root of 9x to the 4th, and we write it as 3x squared, what we're really doing is we're assuming that we can look at it like this. Okay, but we just kind of went ahead and did it. Likewise, if we have the square root of 1/4 and we write it as 1/2, it's no different from if we took it and said, oh, let's do that to it and that to it. So what I'm getting at is in a previous section, we already actually applied these rules, this one and this one. We just didn't formally talk about it. Well, now we're going to talk about it. Okay. Now, we're going to be using these rules in a situation known as simplifying a radical. And I want to define what we mean by simplifying a radical. That doesn't necessarily mean that when we're done simplifying it, the answer's going to look simpler than the original problem. Simplifying the radical means we want to take everything we possibly can outside of the radical so that the number inside is smaller than it was, if at all possible. Okay, now the square root of 28. We want to simplify this radical. 28 is not a perfect square. So I can't just, square root of 28 and get some decimal number. It would be irrational and it would keep repeating, and we don't want that. But what we could do is we could rewrite the square root of 28 as the square root of 4 times 7, being 28. Then, using these new rules, we could split it up as the square root of 4 times the square root of 7. So what I'm doing is I'm getting factors that are perfect squares. Unsquaring them, I get 2 square roots of 7. So the square root of 28 simplified is 2, oops, I wrote the wrong thing there. I wrote 2 square roots of 2, even though I said 7. So the square root of 28 equals 2 square roots of 7. That's the simplification of the radical. All right. Any questions about what happened there? Okay, let's take a look at another example. We have 9 times the square root of 54. Well, 54 is 9 times 6. Why did I break it apart that way? Because 9 is a perfect square. So now I've got 9 times the square root of 9 times the square root of 6, which is 9 times, well, the square root of 9 is 3 times the square root of 6, so I get 27 square roots of 6. So 9 square roots of 54 simplifies down into 27 square roots of 6. So again, we've reduced the amount inside the radical, so we've simplified it. Okay, let's see here. The cube root of 40. Well, now my index is a 3 instead of a 2. So I'm looking for factors that are cubes rather than squares. Well, 40 is 8 times 5. 8 is a cube. So we could split it up. The cube root of 8 times the cube root of 5. The cube root of 8 is 2. So I get 2 cube roots of 5 as my final answer. Any questions about that?
No.
All right. Let's take a look at the 4th root of 32. Well, let's see. 32 is 2 times 16, which is 2 times 2 times 8, which is 2 times 2 times 2 times 4, which is 2 times 2 times 2 times 2 times 2. Oh, it's 2 to the 5th power. Okay. Now, I'm going to rewrite that as 2 to the 4th times 2 to the 1. And the reason for that is because the 4th root of 2 to the 4th is what? It's 2 on the outside, and this 2 is left inside. So if my exponent matches my index, they reduce down to a 1, and I have something to the 1 power, which means I just have the base, but it's outside now. Does that make sense?
Sort of.
Sort of. Okay. Well, I'm gonna keep driving that point home here. So we'll see if we can get this to work. All right. Directions say simplify each radical expression. All variables represent positive real numbers. So we don't need to worry about absolute value bars in this context. Okay. My index is an implied 2. 50 is 2 times 25, which is 2 times 5 squared. I'm going to rewrite the radical as 2 times 5 squared times x squared. Okay. I could separate that and make it the square root of 2 times the square root of 5 squared times the square root of x squared. Well, the square root of 2 isn't going anywhere. But what about the square root of 5 squared? Wouldn't that just be 5?
No. Wouldn't it?
Just this piece, wouldn't that be just 5? The square root of 5 squared?
No.
Are you saying no or yes?
I'm not really sure.
You're not following. It's okay. It's okay. All right. Let's backtrack a little bit. Okay, we'll come back to that. What's the square root of 25?
5.
What's the square root of 5 squared?
25. Oh, no. They got me.
What would it be?
Would it just be 5 still?
Yeah. In fact, let's do this. This has an implied 2 there all the time, right?
Yes.
Let's take this expression and let's write it using exponents. Wouldn't that be 5 to the 2 over 2 power?
Yes.
Which would be 5 to the 1 power, which would be 5?
Yeah. So it would be 5.
So if the index and the exponent match, they reduce down to just the base outside.
Okay, that makes more sense.
Okay, let me say it this way. The nth root of a to the n equals a if a is greater than or equal to 0. What am I saying? If the base is positive and the index and the exponent are the same, they reduce down to just a.
Yeah. Okay, so that makes more sense.
Okay, good. And I think I just kind of jumped over that thinking that you'd see it, but that's okay. Now, if this base is negative, but these are odd index and exponent, then it also works. But if this is negative, if the base is negative and we're taking it off an even root, then of course it's not real and we can't do that. Okay, now back to this problem. Okay, 50 is 2 times 25, which is 2 times 5 squared. So I could write this as 2 times 5 squared times x squared, the square root of all that. You okay with that?
Yes.
Now, the square root of 2 isn't going anywhere. But what's the square root of 5 squared?
It would just be 5.
Outside. What's the square root of x squared?
Just x?
Outside. And my final answer, 5x square roots of 2.
Okay.
Now, I skipped a step here. Doing it the longer way, I would have rewritten it, and this is what I did earlier. And then I said, okay, that's the square root of 2, that's 5, that's x. Rather than splitting it apart, because I knew they were all factors, I just dealt with them one at a time. Okay. And we're going to do some even further shortcuts eventually here. All right, now, but again, if you get lost in something, please let me know. We've got the square root of 75, b to the 8th, c. Okay. So what I'm looking for are squares and leftovers. 75 is 3 times 25. 25 is a square, isn't it?
Yeah.
B to the 8th could be b squared times b squared times b squared times b squared, and then times c. So everything up there is a square or less than a square. Okay. And I wrote 25. I could have written it as 5 squared, either way. So now we're going to go through and break it apart. What's the square root of 25? That's 5 outside the radical. The square root of b squared is b. 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 And the 3 and the c are left inside. So I get 5b to the 4th square root of 3c.
All right.
You okay with that?
Yes.
All right. Now, even that seems like an awful lot of work. Let's consider some things here. What's the square root of b squared?
B.
What's the square root of b to the 4th?
B. Would be square, wouldn't it? Yes.
What's the square root of b to the 6th?
B to the 4th? No. B to the 3rd?
Right? Because
You forgot the 2. Yeah.
okay. Whoops. What's the square root of b to the 8th?
B to the 4th?
Right. So let's go back here and let's look at that again. 75 b to the 8th c. The square root of 25 is 5. The square root of b to the 8th is b to the 4th. So I don't need to break it down all the way like I did there. Okay?
Yeah.
Right,
So
yeah. Go ahead.
To make it easier to think this out, kind of like divide the 8 over the 2 and then
Yep.
make it, and then kind of just get that answer. So it makes it
Exactly.
simple then. Okay.
Exactly, because if you write it in exponential form, you're doing that. You're taking that divided by that.
Yes, that makes it more easier to understand.
Good, good. Now, what about this? What about the square root of b to the 9th? Well, now we've got issues. But what I could do is I could rewrite it, breaking it apart with something that's a multiple of that 2 and leftovers. You see what I'm saying?
So you're just basically expanding the equation a little bit.
Yeah, the expression, yeah. So then this would be b to the 4th square roots of b.
Okay.
So I want my exponents to either match the index or be multiples of the index and then leftovers. And the leftovers get stuck inside.
Okay.
Now let's see if we've got that. Okay. How about this? The 5th root of 64, x to the 10th, y to the 5th. 64 is 8 times 8, which is 2 times 2 times 2 times 2 times 2 times 2, which is 2 to the 6th power. Okay? But I'm going to consider it 2 to the 5th times 2 to the 1 because I want my exponent to match my index. So now I'm going to rewrite that expression as 2 to the 5th times 2 to the 1 times x to the 10th times y to the 5th. Now, x to the 10th, 10 is a multiple of the index. Y to the 5th, 5 matches the index. So I wrote everything as something raised to a power that matched the index or a multiple of the index and then leftovers. So let's see how that's going to work. What's the 5th root of 2 to the 5th?
2.
Outside.
Yes.
What's the 5th root of 2? It's not going anywhere. What's the 5th root of x to the 10th? That would be x to the
First? No. 2.
And then the 5th root of y to the 5th would be,
Just y.
and we've got the 5th root of 2 left inside.
Yeah.
You getting it?
Yes, because you can't do anything to the 2 because it has a low power than it originally is. So then you would just have to skip that and leave that left over.
Yep, because its power is less than the index.
Yes.
All right. Let's see here. Let's do this one. The 4 times the cube root of negative 81a to the 5th power. Wait, it's a to the 3rd power. My bad. Yeah, okay. Now, negative 81 is negative 1 times 81, right?
Mm-hmm.
Which is negative 1 times 9 times 9, which is negative 1 times 3 times 3 times 3 times 3, which is negative 1 times 3 to the 4th. But my index is a 3, so I'm going to write it as negative 1 times 3 cubed times 3 to the 1 power. And I don't really need to put that 1 on the 3 to the 1 power, but I'm just emphasizing where it came from, okay? So now I've got 4 times the cube root of negative 1 times 3 cubed times 3 times a cubed. What's the cube root of negative 1?
You can do this. It wouldn't just be left over.
Yes, you can. Negative 1 cubed is negative 1, so the cube root of negative 1 is negative 1, because negative 1 times negative 1 times negative 1 is negative 1. Have I lost you there?
No, I understand that now.
Okay, so I've got 4 times negative 1 times 3 times a times the cube root of 3, or negative 12a cube roots of 3. The 4 was out there to start with. The cube root of negative 1 is negative 1. The cube root of 3 cubed is 3 outside. The cube root of a cubed is a outside, and then this is stuck inside. You all right with that?
Yes.
Okay, excellent. Let's look at the square root of 363. Okay. Says simplify each radical expression. All variables represent positive real numbers. There's no variables in this problem, but there will be. So my index is a 2. So I'm looking for squares or fourth powers or sixth powers or eighth powers and leftovers. Well, 363 is 3 times 120. No, 121, not 127. I think that's right. Let's see. 120, yeah, 121, which is 3 times 11 times 11. So this would be 3 times 11 squared. Okay. So I've got squares and leftovers. The 3 is not going anywhere. What's the square root of 11 squared? It's 11. So I get 11 square roots of 3.
Okay.
So
Sorry, I'm just trying to catch up and write everything down.
that's fine. That's fine. No problem. I can go as slow or as fast as you want. It's all
No.
about you today.
Yeah, the snowstorm's kind of messing with everyone's Zoom.
Oh, is it?
Yeah, my little sister wasn't able to meet her Zoom meetings at all today.
Mine was really weird. I got online there and we were all there and nobody could hear me and I couldn't hear anybody else. And so I finally called somebody and they were like, yeah, we can't hear you. And so I had to reboot everything and eventually got it all figured out. But that's why I asked you at the beginning if you could hear me, because I thought, oh.
Oh, you know, yeah, I can hear you. I had trouble seeing you for like a little bit. Then you came back.
Yeah, yeah. Okay, we good to go on to another one?
Yes.
All right. Let's take a look at, let's see, this one. The cube root of 280, a to the 5th, b to the 6th. So 280 is 28 times 10, is 4 times 7, times 2 times 5, is 2 times 2 times 7, times 2 times 5, is 2 cubed, times 5, times 7. So basically what I've done is the prime factorization of 280.
Okay.
Broke it down to all prime factors. You probably haven't done that since Math 50 or 75 or whatever.
I didn't take math 50 years.
Well, or just a class at that level way back when you first learned about fractions and stuff. But anyway, you follow how I got that.
Yes.
All right. My index is a 3. So now I'm going to write this as 2 cubed times 5 times 7 times a cubed times a squared, because I can only take one a cubed out of that, and the a squared is going to be leftovers. B to the 6th, because 6 is a multiple of the index. Okay.
Okay.
So, oh, I left out my index. Bad, bad. What's the cube root of 2 cubed?
Wouldn't it just be 2 on the outside?
Exactly. This isn't going anywhere. This isn't going anywhere. What's the cube root of a cubed?
Would just be a on the outside?
This isn't going anywhere. What's the cube root of b to the 6th?
2. B to the 2nd.
Okay. And now I'm going to multiply together what's left inside. 5 times 7, 35a squared. And there's my answer. So the index is what drives the problem. You want everything inside to match the index or multiples of the index. They're the powers, that is.
Yeah. Otherwise, the whole equation won't form out properly as what you want it to be.
Say that again. I'm sorry.
If you didn't have the index put in, then you wouldn't have the right outcome of the situation of your equation.
Okay. Let's see here. Now let's take a look at a radical that's got a fraction in it. So I could split this up into these two things, which would then give me that. Does that make sense?
Yeah.
Okay. Let's take a look at this one. The fifth root of 2 over 243. That's equal to the fifth root of 2 over the fifth root of 243. Well, I can't do anything with the fifth root of 2, but let's take a look at 243. That's 3 times 81, which is 3 times 9 times 9, which is 3 times 3 times 3 times 3 times 3, which is the fifth root of 3 to the fifth. So my numerator is the fifth root of 2. What's my denominator going to be?
3 to the 5th? Or just 3?
Just 3, exactly.
Sorry, I got lost.
That's okay,
I was
sorry.
supposed to be at.
Sorry. So we've had 3 big rules in this chapter. The first 2 I gave you, I think maybe even the first day or so. When you're taking an even root, you can't take an even root, can't even talk today. You can't take an even root of a negative number and get a real answer. That was the first rule. The second rule, when you take an even root of a number, you can't get a negative answer. So with even roots, the radicand can't be negative and the answer can't be negative. And the third rule is the one we looked at today, this thing about the nth root of a to the n is a if a is greater than or equal to 0. That's the thing we've been doing over and over here, getting the exponent to match the index so that we can undo them and take the base outside the radical. Okay? And those 3 rules, you want to get those under your belt, so to speak. How about this one? The square root of b to the 4th over 64 a to the 8th. Well, that's the square root of b to the 4th over the square root of 64 a to the 8th. But everything in there is either a square or a multiple, exponent-wise. What's the square root of b to the 4th?
Wouldn't it just be b? Or b to the second?
There you go. What's the square root of 64?
Wouldn't it just be the square root of 64?
Mm-hmm. What is that?
Be 8.
Okay. What about the square root of a to the 8th power?
Would it just be 8a to the power of 2? Or wouldn't it just go to 4?
Right? Because the square root of
4.
a to the 8th. Okay.
Yep, I'm not starting to understand it better. I'm sorry.
It's kind of it's like you're out in center field and a fly ball's coming to you. I got it. Oh no, I don't got it. No, wait, maybe I've got it. You know, it's like you get it and then you don't. It's okay.
It's been a really hard morning, so I'm like,
that's okay. Sorry.
Slow.
We'll get it into your head. It just takes some practice, and that's just fine. Sorry, it was a hard morning for you.
It's all right.
You have to shovel a car out of the snow or something?
Yeah, that and a lot more.
Oh, sorry to hear that. Okay. This says, simplify each expression. All variables represent positive real numbers. Well, I'm glad that you made it to join me. I was getting lonesome all by myself here. All right. So now, instead of taking a fraction under a radical and splitting it up into 2 separate pieces, I can take this and make it into 1 fraction. Since they have the same implied 2 as an index, I can put them together. In other words, instead of doing that, we're doing We're going from here to here. Why would I want to do that? Because now I can reduce what's inside there. 128 divided by 2 is 64, and the square root of 64 is 8. So because these had the same index, I could write them as a single fraction inside the radical, reduce it, and then simplify it.
All right.
Let's take a look at another example of that. Let's say I've got the square root of 75 y to the 5th power over the square root of 3y. Okay, and again, the instructions said all variables represent positive real numbers, okay? This could be written as the square root of the quantity 75 y to the 5th over 3y.
Mm-hmm.
But that could be reduced down to the square root of 25 y to the 4th.
Because then you would subtract from the y. Yeah.
What's that?
No, I'm just understanding how you got to y4, and then I just looked at you just subtracted both y's to get the y to the 4th.
Yes.
Yeah.
Okay, what's the square root of 25?
5 on
What's the
y.
square?
Oh.
Go ahead.
5y squared.
Exactly. Good job. Okay. Good to go on or still writing?
No, I'm good.
Okay. Cube root of 243 x to the 8th divided by the cube root of 9x. Since the index on top and bottom are the same, I can write this as the cube root of 243 x to the 8th over 9x.
Mm-hmm.
Now the question is, does 9 go into 243 evenly? And I think it does. Let's see. 243 divided by 9 is 27. So this becomes the cube root of 27 x to the 8 minus 1 x to the 7th. Okay.
All right.
We good to go on?
Yes.
X to the 7th, I'm going to write as x to the 6th times x, because 6 is a multiple of the index, and I got 1x left over.
Yes, so you're able to.
And 27 is a cube. So what's the cube root of 27?
Wouldn't it be 3?
Mm-hmm. What's the cube root?
3x to the 2nd?
Yep, and then the leftovers.
Yep.
Take out and leftovers. You want to take out everything you can. That which you can't is stuck inside. All right?
Yeah.
Now it says, simplify by combining like radicals. Let me ask you this. What's 2x plus 3x?
5x.
What's 2 square roots of 11 plus 3 square roots of 11?
5 to the square root of 11.
Excellent. Okay. What's 11 square roots of 3 plus 2 square roots of 3?
13 to the square root of 3.
Okay. Sorry, I shouldn't have taken that away so fast. All right. What's 30 cube roots of 6 minus 10 cube roots of 6?
20 to the square root of 30 to b.
That's a 6, sorry.
Oh, 6, my bad.
Okay, so you'd say 20 cube roots of 6. You said to the square root, but it's a cube root.
Oh, my bad.
That's okay. It's okay. I'm just being picky. Now, let's say we've got 9 plus the square root of 45 plus the square root of 20 plus 16. And again, it says simplify by combining like radicals. What we want to do is we're going to simplify each term as much as we can first. Now, the 9 and the 16, we can't do anything with them yet. All we can do is put them together eventually. But the square root of 45 would be 9 times 5. The square root of 20 would be 4 times 5. And why did I take 45 and write it as 9 times 5? Because 9 is the biggest square that's a factor.
Yeah, so then you're able to add and subtract and multiply for each one of them. So you're just simplifying the whole thing out.
All right, so what am I going to do here? What's the square root of 9?
Square root of 9.
Yeah, what is that?
3.
I've got 3 square roots of 5. Square root of 4?
2.
2 square roots of 5 plus 16. Okay. These go together. And those go together. Oops. And there's my final answer. But initially, these didn't look like radicals. I had to simplify them to identify that they were. And sometimes they will be, and sometimes they won't be.
That makes more sense.
All right with that?
Yes.
Okay. Square root of 20 plus square root of 125 minus square root of 80. My index is a 2, so I want squares to undo. So this will be 4 times 5. This will be 25 times 5. And this will be 16 times 5. Now, I'm skipping the whole part of breaking it down and prime factors and doing all of that. If you want me to, I'll go back and do that. But I wanted to just kind of cut to the chase here.
No, go ahead.
Okay, so what's the square root of 4?
2.
So I get 2 square roots of 5 plus, what's the square root of 25?
5.
I get 5 square roots of 5 minus, what's the square root of 16?
8. No, 2. My bad. Isn't it 2? Or wouldn't it be 4?
There you go. Third time's a charm. Okay. So these are all like radicals. 2 of something plus 5 of something is 7 of something. Minus 4 of something is 3 of something, the something being the square root of 5.
That's a lot of somethings.
Yeah, sure. That's right. Boy, it is something, isn't it? Okay.
Yep.
All right, now. Simplify by combining like radicals. All variables represent positive real numbers. We have the square root of 80m minus the square root of 128m plus the square root of 288m. Okay, so again, all of the indexes or indices or however you say that are 2's. So I'm going to break it down into squares and leftovers. 80 is 16 times 5 times m. 128 is 64 times 2 times m. And 288 is 144 times 2 times m. Okay?
Mm-hmm.
What's the square root of 16?
4.
So I get 4 square roots of 5m, because I can't do anything with the 5 or the m. Minus, what's the square root of 64?
8.
So I get 8 square roots of 2m. Can't do anything with the 2 or the m. What's the square root of 144? 12.
12? Yes.
12 square roots of 2m. Oh, these are alike, but this one isn't. So I've got 4 square roots of 5m, and then minus 8 plus 12 would be plus 4 square roots of 2m.
All right. And you can't add them both together because they both have a different m.
Well, different, yeah, coefficient of m, sure. Yeah, they're not like radicals.
Yeah.
All righty. Well, there you go. So I hope your day gets better. Again, no class on Monday, no nothing on Monday. Just keep digging yourself out of the snow. And thanks for joining me. Like I say, I hope your day gets better. I will be back at 1:15 should you have need of me. Otherwise, have a great weekend.
You too. Thank you.
You bet. Take care.
You too.